Octopus Signature Tracer or VI Curve Tracer. This is the documentation of the experience of a hobby project, made with the hope that it could be helpful to others. However, these videos are not intended as tutorials. They only show the development of a personal practice, which may or may not be a good one. Therefore, if you are following along, you are doing so at your own risk. In January 1975, the magazine QST published an article with the title, "The Octopus, an Overall Component Tester for In-Circuit Troubleshooting." An editor's note explains that the article was published before in a naval publication without giving any more information about it. However, the original author was David L. Ludlow. The Octopus is a very simple piece of equipment which, connected to an oscilloscope, can represent the signature of the component even if it is in circuit, provided that the circuit is not powered. The article is worth reading because it explains very well the function of the octopus and how to use it, also showing examples of common signatures. As for the name Octopus, this is quoted from the same article. The unit was originally designed for in-circuit testing of Navy electronics equipment. Since the power cord, oscilloscope leads, and probe cables protruding from various sides of the tester resembles an octopus, it is commonly called just that. The simplest possible octopus would look like this: a step-down transformer and a resistor. The transformer would provide a voltage that is supposed to be safe for the device under test, or DUT for short, while the resistor would also establish the maximum current that could traverse the DUT. According to the original design, the voltage should be about 1 volt RMS and the resistor should be of 1 kilo ohm so that the maximum current could be only 1 milliamp. If the transformer provides instead a higher voltage, that could be reduced with a voltage divider composed by 2 more resistors. The original design already defines the values for these 2 resistors in case of a transformer that can deliver 3.15 volts RMS, corresponding to a half of the common filament voltage for vacuum tubes. This would maintain at about 1 volt the voltage that would affect the DUT. And in case of higher voltages coming from the transformer, it would be sufficient to increase the value of resistor 1, keeping R2 at the same original value. All the oscilloscopes have a vertical input, but the Octopus can be used only if there is also a horizontal input available, which should be configured for overriding the internal sweeping oscillator. The horizontal input of the oscilloscope X must be connected across the DUT, while the vertical input Y must be connected across the current controlling resistor, like the schematic diagram shows. When the energy from the step-down transformer is in the positive phase, the voltage excursion across the DUT is represented on the oscilloscope screen horizontally to the right. However, in this phase, the current traversing the resistor would turn into a negative voltage on the Y oscilloscope probe appearing downwards on the screen. Therefore, if voltage and current are in the same phase, the lower right side of the screen will be used. Everything goes in the opposite direction for negative values. Negative voltages are represented towards the left and negative currents are represented upwards. Consequently, if voltage and current are in the same phase, the top left side of the screen will represent them. However, current and voltage can be out of phase, and in that case, the remaining quadrants of the screen would be used. What is important to observe is that voltage and current are not represented like the usual Cartesian graph because the current appearing in the y-axis is flipped vertically. Online, one could find plenty of alternative projects following the fundamental idea of the original Octopus signature tracer. There are also plenty of commercial products offering similar functionalities, which are known as VI curve tracers, where VI stands for voltage and current. There are a few improvements that would be beneficial for a modern Octopus. The testing voltage should be adjustable in order to better observe a wider range of components. By changing the frequency of the test sine wave, small value capacitors and inductors could be more easily seen. Comparing two identical circuits would also be beneficial. The commercial products may address these needs, but building a personal Octopus is more fun. The owner of the channel ZeroVolt published an interesting implementation that still relies on the mains for generating the probing sine signal. But it offers variable testing voltages and the possibility to compare two circuits simultaneously. The main part of the project from ZeroVolt relies on a voltage divider composed by a resistor in series with a capacitor. This makes calculations more difficult, but it has the advantage of filtering out noise coming from the mains. This is just an adaptation of the ZeroVolt design for a single DUT, and anyone interested is invited to consult the complete original. The adaptation was necessary to use an available transformer and capacitor, as well as common resistor values. Everything has been facilitated by a spreadsheet already made and published by ZeroVolt, but for the sake of curiosity, here are the necessary steps for determining the voltage across capacitor C1, which corresponds to what the DUT would be exposed to. As for determining the maximum current across the DUT, if not assisted by the original spreadsheet, the calculations become too complex, and what is important is to consider that as long as the impedance of the capacitor is significantly lower than the value of resistor R2, one could consider dividing the voltage across the capacitor by R2, obtaining a value surely higher, but close to what could be calculated correctly. Here is the final result installed above the bench. The Octopus is prepared for testing a few components. The desired testing voltage is selected and then it is turned on. The analog oscilloscope is prepared, connecting X and Y inputs. The horizontal sweep is already set for external. Open circuit. Short. Capacitance. Inductance. Diode with the red probe attached to the cathode. Now the red probe is attached to the anode. Zener diode with the red probe attached to the cathode. now attached to the anode. The same test is repeated on a digital oscilloscope configured for XY curve mode. The digital oscilloscope is calibrated horizontally, which allows to determine that this is a 5.1 volts centered diode.